Today, we are doing something a little different, something that I, frankly, have been looking forward to since we first got this stack of research papers on our desk.
Mm-hmm.
Usually, we take a look at a broad concept, maybe a business trend or a historical event. But today we are going microscopic. We are going right into the engine room of the human body.
It's one of my favorite places to be. And you're right, this isn't just a biology lesson. I think that's the first misconception we need to clear up right away. This is physics.
Yes.
This is math. This is the chaotic reality of how we stay alive from second to second.
Exactly. We are looking at Chapter 40 of our source material, and it's titled Principles of Gas Exchange, Diffusion of Oxygen and Carbon Dioxide Through the Respiratory Membrane.
A bit of a mouthful.
It is a mouthful, and look, I know that sounds like a dry title. It sounds like something you sleep through in a lecture hall at 8 a.m. But when I started reading the source material, I had this moment where I realized, oh my God, there is no tiny machine in my lungs pumping air.
Right. There's no fan. There's no little conveyor belt taking oxygen molecules and handing them to the red blood cells. It's not an assembly line.
It's just chaos. It's just molecules bashing into each other. So our mission today, and we're being very deliberate about this, is to unpack every single line, every concept in this chapter.
Every line.
We're going to look at the gas laws, the anatomy of this incredibly thin membrane, and this mind-bending concept of ventilation-perfusion ratios.
It is mind-bending, and I think the hook here, for anyone listening, is realizing that respiration is technically just molecules bouncing around randomly. We are kept alive by statistical probability.
It's terrifying and cool at the same time. It really is. So let's start at the very bottom, Section 1 of our outline, the physics of gas diffusion, the molecular basis. Talk to me about this. What is actually happening when I take a breath?
Okay, so we have to strip away the biology for a second and just look at the physics. The chapter opens by defining diffusion simply as the random motion of molecules.
It's random. That's the key word, isn't it?
Completely random. The source details this beautifully. It explains that the energy for diffusion comes entirely from kinetic motion. Unless you are at absolute zero temperature, which is, minus 273 degrees Celsius, every molecule in the universe is vibrating, moving, and crashing into things.
So visualize this for me. I've got oxygen molecules in my lungs right now. What are they doing? Are they just sort of floating peacefully?
No, they are flying. Picture a billiards table, but in 3 dimensions. And imagine you have 1,000,000 balls, all shot at the same time at high speed. They are bouncing off the rails, hitting each other, spinning away in new directions.
Okay.
That is a gas. They move in a straight line until they hit something, another molecule or a wall, and then they ricochet off in a new, completely random direction.
Okay, so if it's all random bouncing, how does oxygen actually get where it needs to go? Why doesn't it just bounce back out of my mouth? Or just stay in the lung? That seems like a design flaw.
It does, but that's where the concept of net diffusion comes in. This is crucial to understand. So imagine you have a chamber, and it's divided in half by a permeable screen. Side A has 1,000,000 gas molecules. Side B has only 10.
Okay. So we have a high concentration on side A and a very, very low concentration on side B.
Right, a steep gradient. Now, because the motion is random, molecules on side A are going to bounce across that dividing line into side B constantly, just by chance.
Okay.
And molecules on side B will also occasionally bounce into side A. But simply because there are so many more on side A, the probability is that far, far more will cross from A to B than from B to A.
So the net movement, the overall flow, is from high to low.
Exactly. It's not that the molecules want to go there. They aren't seeking empty space or anything like that. It's just math. It's a statistical certainty. The concentration gradient drives the net diffusion. And figure 40:1 in our source actually shows this beautifully. You see these arrows pointing both ways, but the arrow from high to low is massive compared to the tiny one going the other way.
It's a numbers game, pure and simple. Okay, so that's the motion. But in physiology, and in this text specifically, we don't usually talk about concentration of gases as much as we talk about pressure. I see this term everywhere in the chapter, partial pressure, PO2, PCO2. Let's unpack that. What is pressure really in this context?
Pressure is impact. Literally, if you have a gas in a container, the pressure is the cumulative force of all those billions of molecules slamming against the walls of the container every second.
So more molecules means more slams.
Exactly. The more molecules you have in that fixed space, the more impacts you get against the walls, the higher the pressure. So pressure is directly proportional to concentration.
Okay, that makes sense.
If you double the number of molecules in a jar, you double the number of impacts against the glass, so you double the pressure. And this leads us right into Dalton's law, which is absolutely essential for understanding the air we breathe.
Let's run the math on air. Because air isn't just one thing. We treat it like it is, but it's a mixture.
It's a stew, a gaseous stew. At sea level, the total atmospheric pressure is 760 millimeters of mercury millimeter Hg. That's the standard unit of measurement we'll be using. And that number represents the weight of the entire atmosphere, miles and miles of air crushing down on us.
Wow.
Now, air is roughly 79% nitrogen and 21% oxygen. There are trace amounts of other things, but let's ignore those for now.
I always forget how much nitrogen is in there. It's mostly nitrogen. It feels like the silent partner in all this.
It's almost all nitrogen. It's the filler gas. So if we apply Dalton's law, each gas contributes to that total 760 pressure in proportion to its concentration. So to find the partial pressure of nitrogen, or PN2, you take 79% of 760.
Which comes out to about 600 millimeter Hg.
Right on the money. And the oxygen.
Okay, 21% of 700 Gs, doing the mental math, is roughly 160 millimeter Hg.
That's your PO2. And this is why this matters. In respiratory physiology, we track these numbers like a stock ticker. The PO2 starts at 160 in the air outside your body, but as it moves into the lungs, into the blood, into the tissues, that number changes. And gas always moves from a region of high partial pressure to a region of low partial pressure.
It flows downhill, like water.
Exactly. If the pressure is 160 outside and 100 inside, oxygen flows in. If it were somehow reversed, oxygen would flow out. It is that simple. It's a physical law.
Okay, so we have gas bouncing in the air. That makes sense. But here is where it gets really interesting. And I'll admit, slightly confusing for me initially. We aren't filled with air. We are filled with blood. We are mostly liquid. How do we talk about gas pressure in a liquid?
This is a stumbling block for a lot of people, and it's a really good question. It's section 2 of our deep dive. Gas is dissolved in water and tissues. How can a dissolved gas have pressure?
Yeah, it feels like it should just be gone, part of the water.
But think back to the billiard balls. Even when an oxygen molecule dissolves into water or blood plasma, it doesn't just stop. It's still a tiny energetic particle. It's still moving. It's still bouncing off water molecules and the walls of the blood vessel. So it still exerts pressure.
But there's a catch, right? The text makes a big deal about this. It's not just about how many molecules are in the water. It's about how much the gas likes the water.
Correct. This is where we bring in Henry's law. The formula, and we'll break it down, is partial pressure equals the concentration of the dissolved gas divided by its solubility coefficient.
Solubility coefficient. Okay, that sounds like a variable we really need to define. What does that mean in simple terms?
Think of it as a measure of how easily a gas dissolves. Or you could think of it as attraction. Some gases are hydrophobic, they hate water, they want to escape. So even a small amount of them dissolved in water creates a huge amount of pressure because they're constantly banging against the surface trying to get out.
They're restless.
Very restless. And some gases love water. They're happy to just hang out, dissolved. They don't generate much pressure.
Okay, so let's look at the numbers. The source gives a hierarchy, and it is fascinating because you can see how evolution clearly utilized this. At body temperature, what's the solubility coefficient for oxygen?
The value for oxygen is 0.024.
Is that high or low? I have no frame of reference.
It's pretty low. Oxygen isn't a huge fan of water. It takes some force, some pressure to keep it dissolved. It's one of those restless gases.
Okay, now compare that to carbon dioxide, CO2.
Now look at the number in the text for CO2. Its coefficient is 0.57.
Whoa, that is... Let me look at those numbers again. 0.024 for oxygen versus 0.57 for CO2. That's more than 20 times higher.
It is more than 20 times as soluble as oxygen. This is the aha moment of this section. This is one of the most important facts in respiratory medicine.
Why? What does that mean practically?
It means because CO2 is so soluble, you can pack a ton of it into the blood, and it exerts very little pressure compared to oxygen. It's happy to sit there. It doesn't fight to get out. So for the same number of molecules, carbon dioxide is basically quieter in terms of pressure than oxygen.
So it generates less push to escape.
Yes. CO2 exerts 120th the pressure of oxygen for the same concentration. And this dictates everything about how we move these gases. We need a big pressure difference, a big push to move oxygen because it's stubborn. We don't need much of a pressure difference to move CO2 because it flows like water. It's eager to move.
That explains so much about the pressure gradients we'll see later. They're not symmetrical. It's
Yeah.
all about the solubility. Okay, so we've got Henry's Law. Now let's talk about another gas that we usually ignore but is actually a huge player here, water vapor.
Right. Section 3, you breathe in air. Unless you are in a rainforest or a steam room, that air is relatively dry. But the second it hits your nose, your throat, your trachea, your body attacks it with moisture.
It humidifies it.
Instantly. Water molecules from the surface of your mucous membranes evaporate into the air you just inhaled. And just like any other gas, this water vapor exerts its own partial pressure. We call it vapor pressure, or pH2O.
And this isn't a variable number, is it? Inside the body, it's fixed, right?
At body temperature, which is a stable 37 degrees Celsius, it is a rock-solid constant. 47 millimeters of mercury, always.
So why is that number important? Why do I need to know 47?
Because, remember, the total pressure can't go above 7.6 XT at sea level. That's the atmospheric limit. If you add 47 millimeter Hg of water vapor to the mix, you have to subtract that space from the other gases.
Oh, it dilutes them.
It absolutely dilutes them. You are essentially making the oxygen concentration lower before it even reaches your lungs proper. So that 160 millimeter Hg of oxygen we calculated for dry air, it immediately drops.
It's like a toll tax for breathing. We lose some oxygen pressure just by humidifying the air.
Exactly.
Yeah.
The nitrogen pressure drops, the oxygen pressure drops, everything shifts to make room for the water vapor. It's a non-negotiable part of the system.
Okay, let's move to section 4. We've set the stage with the laws. Dalton, Henry, vapor pressure. Now we need to look at the master formula for diffusion in fluids. Because eventually this oxygen has to swim through the wet membranes of the lung. What determines how fast that happens?
Right, this is where it all comes together. The source text gives us a formula for the diffusion rate, which it calls D, and it depends on a few key factors. If you want to understand lung disease, you have to understand these factors. Let's break them down one by one.
Let's do it. Factor number 1.
The pressure difference. We'll call it delta P. This is the gas pedal. This is the engine. The bigger the difference between the pressure in the lung air and the pressure in the blood, the faster the gas moves. If the pressure is equal on both sides, nothing moves. Net diffusion stops.
Makes sense. Factor 2.
The cross-sectional area, let's call it A. Think of this as the size of the door, or the width of the hallway. The wider the door, or the more surface area you have in your lungs, the more gas can get through at once.
Factor 3.
Solubility. Yes, we just touched on this. The more soluble the gas, the faster it moves through the fluid membrane. It doesn't get rejected by the water. It just zips right through.
Okay. Factor 4.
Distance. Now, this one is in the denominator of the equation. This is the enemy. This is the thickness of the membrane the gas has to cross. The farther the gas has to swim, the slower the rate of diffusion. You want this distance to be as close to 0 as possible.
And finally, molecular weight.
Right. Molecular weight, MW. Heavier molecules are just more sluggish. They have more inertia. It's harder to get them moving. So the rate is inversely proportional to the square root of the molecular weight. It's a smaller factor than the others, but it's there.
But here is the kicker comparison. If we take all these factors, especially solubility and molecular weight, and combine them to get a diffusion coefficient, and we compare oxygen to other gases.
This is where it gets really interesting. Let's look at the leaderboard. If we set oxygen's diffusion rate as our baseline, so it's 1.0,
What's carbon dioxide?
it's 20.3.
20.3. So it moves 20 times faster than oxygen, even though it's a heavier molecule.
Even though CO2 is heavier than oxygen, its solubility is so overwhelmingly high that it just shoots through the membrane. The solubility advantage completely swamps the weight disadvantage.
So practically speaking, if your lungs are damaged, say the membrane gets thick with scar tissue or fluid, oxygen is going to be the first thing to fail, right? Because CO2 is a super diffuser.
That is a key clinical pearl. Absolutely. Yeah. If a patient have a diffusion problem, they will have low oxygen. We call that hypoxia, long before they have high carbon dioxide. CO2 can almost always find a way out. Oxygen struggles.
Wow. That is fascinating. It's like CO2 has a VIP pass to get out of the body. Okay, so we've got the physics down. Now let's talk about the environment. We touched on this with the humidification, but Section 5 makes a big point. The air in your alveoli, the deep lung sacs where the magic happens, is not the same as the air in the room.
It's completely different. And this is a common misconception. We have a tendency to think we breathe in fresh air, it goes to the bottom of the lung, we extract the oxygen, and then we breathe out the waste. But that's not how it works at all.
No. The text lists 4 reasons why alveolar air is distinct. We already mentioned humidification. That's number 1. What's number 2?
Number 2 is partial replacement. You don't empty your lungs completely when you exhale. If you did, your lungs would collapse, and it would be incredibly hard and energy intensive to inflate them again from zero.
Right, we have a reserve of air that's always there.
Exactly. So with every breath, you are always mixing a small amount of fresh air with a large amount of old, stale air. You are just topping off the tank, not replacing the whole thing.
Okay, reason 3.
Oxygen is constantly being absorbed. It doesn't just sit there waiting for the next breath. The blood is like a vacuum cleaner, sucking it out of the alveoli every millisecond.
And reason 4.
Carbon dioxide is constantly being dumped in from the blood, so the soup in the alveoli is this dynamic mix of fresh air, water vapor, disappearing oxygen, and appeaing CO2.
So let's look at the actual numbers from table 40-1 in the text. This really drives it home. Atmospheric air has an oxygen pressure of 159 mmHg. By the time it's humidified, it drops to 149. But what does it weigh down in the alveoli?
It drops all the way to 104 mmHg.
That's a big drop, from 159 in the atmosphere down to 104.
It is a huge drop, and that 104 number is the magic number for arterial blood. That's the target.
Yeah.
If you measure the oxygen partial pressure in your arteries, it should be very close to 104.
Okay. And meanwhile, CO2, which is basically 0 in the atmosphere, shoots up to what in the alveoli?
It appears at 40 mmHg.
So the environment down there is a steady state of 104 oxygen and 40 carbon dioxide.
Ideally, yes. In a healthy lung at rest, that is the set point. That's the environment the blood is seeing.
And this leads us to section 6, the stability of this air. I found this really comforting, actually. The text mentions functional residual capacity, or FRC. Can you explain why this slow renewal of air is such a good thing?
Imagine if your blood gases changed wildly every time you took a breath. If with every inhalation, your oxygen shot way up, and with every exhalation, it plummeted.
That sounds awful.
It would be a roller coaster for your brain and your tissues. Your chemical sensors in your arteries would be going haywire.
We'd be lightheaded constantly or passing out.
Exactly. The FRC is the volume of air left in your lungs after a normal passive exhale. It's about 2,300 milliliters. But a normal breath, your tidal volume is only about 500 milliliters, and only about 350 of that new air actually reaches the alveoli.
So you're only replacing a tiny fraction with each breath.
About 1/17 of the total air. This means the large volume of alveolar air acts as a buffer. It's a large tank of gas that changes its composition very, very slowly. Figure 42 in the text shows this beautiful exponential curve. If you breathe a different gas, it takes about 17 seconds just to replace half the old gas in the alveoli with normal breathing.
So if I hold my breath for a few seconds, or if I'm talking and not breathing rhythmically like I am right now, my blood oxygen doesn't crash immediately.
Precisely. It provides stability. It stabilizes the whole respiratory control mechanism. It keeps that soup consistent. It prevents sudden shocks to the system.
I like that. The alveolar soup. Now, section 7 gets into the dynamics of this soup. It's a battle, isn't it, between supply and demand?
It's a dynamic equilibrium, and the two main gases behave very differently. Let's look at oxygen first. The graph in figure 40-4 is key here. The partial pressure of oxygen in your alveoli is determined by two competing forces. How fast you breathe it in, which is ventilation, versus how fast your blood sucks it away, which is absorption.
So normally we sit at that sweet spot of 104 mmHg. That's where the curves meet. What happens when I get on a treadmill and start running?
When you exercise, your muscles burn oxygen like crazy. The absorption rate, the rate at which your blood is demanding oxygen, jumps. Say from 250 milliliters per minute at rest to 1,000 milliliters per minute during a jog.
So the demand quadruples.
If your ventilation stayed the same, your alveolar oxygen would plummet. The blood would literally suck the lungs dry of oxygen. The pressure would drop towards venous levels.
So I have to breathe more just to stay in the same place.
You have to increase your ventilation fourfold just to maintain that same 104 partial pressure. And the text notes an interesting upper limit here. You can never ventilate your oxygen higher than 149 millimeter Hg.
Because that's the humidified maximum of the air we breathe.
Yeah.
You can't create pressure out of thin air.
Right. You can huff and puff until you pass out, but unless you are breathing from an oxygen tank, you can't get your alveolar PO2 any higher than the PO2 of the air coming in. You hit a hard ceiling.
Now what about CO2? That graph, figure 40-5, looked different. It was a different shape.
CO2 is simpler in a way, but it's more critical for the moment-to-moment regulation of breathing. Its partial pressure is inversely proportional to alveolar ventilation.
Inversely proportional, so as one goes up, the other goes down.
Yes. If you double your breathing rate, you cut your alveolar CO2 in half. If you quadruple your breathing, you quarter the CO2.
Oh, that's a really powerful relationship.
It is. That's why hyperventilation makes you dizzy and tingly. You blow off so much CO2 that your pressure drops from the normal 40 down to maybe 20 or even 15.
And what does that do?
Since CO2 forms a weak acid in the blood, losing it makes your blood more alkaline. It changes your body's pH almost instantly, and that affects how nerves fire and how blood vessels in the brain constrict.
So CO2 is really the gas we use to regulate our breathing because we can control its level so directly and powerfully with our breath.
Exactly. Your brain's respiratory center is exquisitely sensitive to CO2 levels. It's the most responsive lever we have to pull.
Okay, let's shift gears. We've talked a lot about the gases, the invisible stuff. Now I want to talk about the hardware, the respiratory membrane. Section 8. This is the physical barrier that keeps the air and the blood separate, but also intimately close. Figures 47 and 49 describe this anatomy. Paint a picture for me. What are we looking at?
This is one of the true marvels of bioengineering. It's just spectacular. We have about 300 million alveoli in our two lungs, and they are these tiny, tiny sacs, about 0.2 millimeters in diameter. Imagine a honeycomb or a bunch of microscopic grapes clustered together.
And the blood, where does that fit in?
The capillary network that's wrapped around these alveoli is described in the text as a flowing sheet of blood.
A flowing sheet. Not individual pipes or tubes.
It's so dense that it's less like a network of pipes and more like a water jacket surrounding the air sac. The text implies that the capillaries are so close together they basically fuse into a nearly solid wall of blood.
And the gases have to cross this barrier. The text lists 6 distinct layers. That sounds thick. 6 layers sounds like a fortress wall.
It does sound thick, but let's list them and then talk about the mind-boggling reality. So, moving from the inside of the lung, from the air out to the blood, you have 1. A thin layer of fluid and surfactant lining the alveolus. 2. The alveolar epithelium, which is the lung cell itself. 3. The basement membrane of that cell. 4. A tiny, tiny interstitial space between the two structures. 5. The capillary basement membrane on the other side. 6. And finally, the capillary endothelium, which is the blood vessel wall itself.
6 layers.
6 layers, but the total thickness of all 6 combined, on average, 0.6 micrometers.
0.6 micrometers. I'm trying to visualize that. How small is that?
A single red blood cell is about 7 or 8 micrometers wide. So this entire 6-layer barrier is 1/10 the thickness of a single red blood cell.
That is mind-blowing. It's essentially nothing.
It is. The red blood cell actually has to squish and deform just to squeeze through the capillary next to this membrane. That's how incredibly thin this barrier is. It's practically non-existent from a physics perspective.
Okay, and the surface area. If we took all 300 million of these alveoli and flattened them out,
The total surface area for gas exchange is about 70 square meters.
70 square meters.
Yeah.
Give me a real-world comparison. What is that like?
That's the size of a 25 by 30-foot room, or the classic comparison is a racquetball court.
Wow. So we have a racquetball court of surface area crammed into our chest with a barrier that's a fraction of the width of a single blood cell.
And here's the wildest number of all for me. The total amount of blood that is in the lung capillaries at any given instant is only 60 to 140 milliliters.
Wait, what? That's it? That's like a half a cup of coffee.
A half a cup of coffee spread over a racquetball court.
Spread over an entire racquetball court.
Yes. So imagine spilling half a cup of coffee and trying to cover an entire floor with it. The blood is spread so incredibly thin that it creates this massive surface-to-volume ratio. This is why gas exchange happens almost instantaneously in less than a second.
That is incredible efficiency, but it also sounds incredibly fragile.
It is, and that's why it's so susceptible to disease. Which brings us to Section 9. Factors affecting diffusing capacity. What happens when this perfect hardware breaks?
We have 4 factors here again, which mirror the diffusion formula. Thickness, surface area, the diffusion coefficient, and the pressure difference. Let's talk pathology. What happens to thickness in disease?
Think of something like pulmonary edema, fluid in the lungs. That interstitial space, one of our 6 layers, which is normally almost nothing, swells up with water. Now, the oxygen and CO2 have to swim a much longer distance to get from the air to the blood.
So diffusion slows down.
Drastically. Remember, distance is the enemy in that equation. Or think of pulmonary fibrosis scar tissue in the lung. That makes a wall thicker and stiffer. The oxygen just can't get across fast enough to support life, especially during exertion.
And surface area. What's a classic example of losing surface area?
Emphysema. This is what we see in many long-term smokers. The delicate alveolar walls literally dissolve and coalesce. So instead of millions of tiny efficient rooms, you get one giant floppy inefficient room.
So you lose all that internal surface area.
You can lose up to 5-fold of your surface area. It's like closing 80% of the doors in a stadium and trying to get the crowd out. It creates a massive bottleneck. The blood is there, the air is there, but there isn't enough contact patch to make the trade happen efficiently.
Now, the text introduces a clinical measurement here. Diffusing capacity, or DLAC. How do they measure this? Because you can't exactly stick a ruler inside the lung to check the thickness or area.
They use a clever trick. They use a tracer gas, specifically carbon monoxide, CO.
The dangerous stuff.
In very tiny, harmless amounts, it's an incredibly useful tool. Remember how we said oxygen has a back pressure in the blood?
Yeah.
That makes it hard to measure the pure capacity of the membrane because the pressure gradient is always changing as the blood picks up oxygen.
Right.
But carbon monoxide binds so tightly and rapidly to hemoglobin that its partial pressure in the blood plasma stays effectively zero.
So if you inhale a little bit of CO, the only thing stopping it from being completely absorbed into the blood is the membrane itself.
Exactly. The blood is like a bottomless pit for CO. So if you measure how much CO disappears from a single breath, you know exactly how conductive the membrane is. It isolates the hardware problem from any blood flow variables. And then they use a simple conversion factor. The text says DO2 equals DCO times 1.23 to calculate the oxygen capacity.
What are the normal numbers? What's a healthy diffusing capacity?
At rest, the diffusing capacity for oxygen is about 21 milliliters per minute per millimeter of mercury of pressure difference.
Okay, and we have an average pressure difference across the membrane of about 11 millimeter Hg for oxygen. So 21 times 11 is?
About 230 milliliters of oxygen per minute, which, coincidentally, or rather by perfect design, is exactly the resting metabolic oxygen consumption of the human body.
The system is tuned perfectly to meet resting demand.
It provides exactly what we need, with no waste. But look at what happens during exercise. The text says the capacity can jump from 21 all the way up to 65.
It triples. How does the membrane get better during exercise? We don't grow more lungs instantly.
The membrane itself doesn't get thinner or change. But remember those dormant capillaries we talked about. At rest, you aren't using all of your lung. The blood pressure is relatively low, so the very top of your lungs is barely being perfused with blood.
Right.
During exercise, your heart pumps harder, blood pressure rises, and it pops open all those previously closed or collapsed capillaries, especially at the top of the lung. You are recruiting more of your lung into service. You increase the surface area that is actively participating in gas exchange.
Incredible. It's like opening extra checkout lanes at the grocery store when the line gets long.
That is the perfect analogy. And this ensures that even when your blood is rushing through the lungs at high speed, it still has enough time and space to get fully oxygenated because the total contact area has expanded to meet the demand.
Okay, we're arriving at what I think is the most complex, but also the most important part of this deep dive. Section 10, the ventilation perfusion ratio, VA over Q.
The holy grail of respiratory physiology. If you understand this, you understand most lung diseases.
Let's break it down. VA is alveolar ventilation, which is the air. Q is perfusion, which is the blood flow.
Right. It is not enough to have air in the lungs. And it is not enough to have blood in the lungs. They have to be in the same place at the same time for anything useful to happen.
It's a dating app. They have to match up in the same location.
Yes. If oxygen is waiting at the restaurant and the blood never shows up, nothing happens. The work of breathing that air in was wasted.
So let's look at the two theoretical extremes the text presents. What happens if VA over Q is 0?
A ratio is 0 when the numerator is 0. So VA, ventilation, is 0. This means an airway is blocked, maybe a piece of food, maybe a plug of mucus. But there is still blood flowing past that alveolus, so Q is normal.
So the blood goes to the lung, looks for oxygen, finds none.
And it leaves exactly as it arrived. It stays as venous blood. It has a PO2 of 40 and a PCO2 of 45. We call this a shunt. The blood shunted past the gas exchange area without getting oxygenated.
Okay, now the other extreme, a VQ ratio of infinity.
This is when the denominator Q, or blood flow, is 0. You have plenty of fresh air getting into the alveolus, but there is no blood flowing past it. Think of a blood clot, a pulmonary embolism blocking the artery leading to that part of the lung.
So the air in that alveolus is perfect, it's fresh, no one is using it.
It's actually better than normal alveolar air. Since no blood is there to steal oxygen or dump CO2, the air in that sac equilibrates with the humidified, inspired air. It has a PO2 of 149 and a PCO2 of 0. But it's completely useless because there's no blood to take the oxygen. We call this physiological dead space.
It's wasted ventilation. You spent energy breathing that air in, expanding your chest, and it did absolutely nothing for your body.
Exactly, it's wasted work.
Now, in a normal, healthy person, we aren't usually at 0 or infinity, but we aren't perfectly matched at a ratio of 1 everywhere either, are we?
No, not at all. Gravity plays a huge role here.
Yeah.
Think about yourself standing or sitting upright. Gravity's pulling your blood down towards the floor.
So the bottom of the lung has lots of blood, more perfusion.
Way more perfusion than ventilation, actually. The blood flow is so high at the base of the lung that the air can't keep up. So the bottom of your lung tends to have a low VQ ratio. It acts a little bit like a tiny shunt. It's inefficient.
And the top of the lung, the apex.
The heart has to pump blood uphill to get to the apex. It struggles against gravity. So the top of the lung has great air, but very poor blood flow. It has a high VQ ratio. It acts a little bit like dead space.
So our normal blood gas readings that we measure in an artery are actually an average of these two imperfect regions and everything in between mixing together.
Yes. The lung is surprisingly imperfect from region to region, but the overall average works out to that beautiful 104 millimeter of Hg of PO2 and 40 millimeter Hg of PCO2. The system works despite its inherent flaws.
But when we get to disease states, this delicate balance falls apart. Section 11 focuses on abnormalities in VQ, specifically in COPD in smokers.
This is tragic physiology. It's where you see these concepts play out in a devastating way. In a chronic smoker with emphysema, you get the worst of both worlds, often in the same lung.
How so?
First, because of chronic bronchitis and inflammation, many of the smaller airways are clogged with mucus. So those alveoli get no air, they become shunts. VQ is 0. Blood passes through unoxygenated. This is what makes the patient's oxygen levels drop and makes them look blue hypoxic.
And the other side of the coin.
The emphysema part of the disease destroys the alveolar walls. When the walls go, the tiny capillaries that live in those walls are gone too. So now you have other areas where you can get air in these big empty cavities, but there is no blood there to accept it. That creates massive amounts of physiological dead space. VQ is infinity.
So the patient is working incredibly hard to breathe. They're panting, using all their muscles.
But a huge portion of that work is completely wasted on ventilating dead space. They are expanding their chest, moving air, but that air isn't meeting any blood. The efficiency of the lung can drop to 1/10 of normal. They are doing 10 times the work just to get the same, often inadequate result.
That is a terrifying image. It really highlights how precise this VQ matching needs to be. It's not just get air in, it's get air to the exact spot where the blood is, right now.
It is. It's a symphony of timing and flow, and in COPD, the orchestra is a mess.
Let's synthesize all of this. We've gone on this incredible journey, from random molecules bouncing in the air, to them dissolving in fluid, to crossing this impossibly thin 6-layer membrane, and finally to this complex dance of matching with blood flow.
It's quite a journey, from pure physics to complex biology and back again.
What is the key takeaway for you, if you had to summarize the deep dive of Chapter 40 in one thought?
For me, it's the thin margins the body operates on. We exist because of a physical barrier that is 0.6 micrometers thick. If it were significantly thicker, we couldn't get enough oxygen to run. If it were much thinner, it might just leak fluid and we'd drown in our own plasma.
Yeah.
And we exist because of the specific solubility of CO2. If CO2 wasn't 20 times more soluble than oxygen, we would need lungs the size of a small car just to get rid of our waste gas.
That's a great point. The fundamental physical constants of the universe seem weirdly tuned to allow this specific solution to exist.
Or rather, we evolved a very specific solution to perfectly exploit those constants.
True. The other way around. Okay, here's a final provocative thought for you, for our listeners to mull over. We treat air as infinite. We walk around, we breathe, we don't think about it, it's just there. But inside your lung, air is a scarce, precious resource. It is carefully and actively rationed against blood flow. Your body is constantly making these tiny microeconomic decisions. Send a little more blood there. No, wait. Constrict that vessel. Send a little more air over here. It is a constant, desperate, and beautiful negotiation to keep that PO2 at 104.
And it does it 12 to 20 times a minute, every minute of your life, without you ever once asking it to.
Incredible. Thank you for guiding us through the physics of the breath.
Yeah.
This is fascinating.
My pleasure. It's an amazing topic.
And thank you for listening. Next time you take a deep breath, maybe visualize those billions of molecules bouncing, dissolving, and racing through that racquetball court in your chest. We'll see you on the next deep dive.